Hello, everybody. Old news where the fossils are old, but discoveries are new. This is Laura Beth. I am your host program, and I on the chat and sure that we get all of these questions answered. And with us, Dr. the museum's research curatology. So say hi, Kristen. Everyone say hi.
Hello, Laura Beth.
Um,
Good to be here. You're cutting in and out a little bit, but I am Christian Kammerer, uh, and happy coverage and analyses this month. Um,
so excited, everyone. So I think we should just dive in. We've got a pretty unique topic this month. Would you say that, Christian?
yeah. So this is like a little different from how we normally do it. So usually, like we're looking for papers that came out usually within just a few weeks before old news to really like have the up to the minute advances in paleontological science. Um, but recently, last week actually, I was at the annual meeting of the Society of Vertebrate Paleontology, which is the biggest sort of global conference of paleontologists who work on animals with bones, vertebrates. Um, and I wanted to talk about something relevant to that because there was a lot of research there, that had me really excited about all the advances being made in our field, and particularly some award-winning research. So every year there's a competition for the basically the best dissertation work by a PhD student called the Romer Prize. And this year it went to research by a PhD student formerly at Brown University, Armida Manafzada, who was working on dinosaurian locomotion and has published several papers on that topic sort of throughout the past few years and some quite recently. I just thought it was such a neat topic, like understanding how prehistoric animals move and sort of in a broader sense, like how they lived. Like so often when we're, presenting our new discoveries, it's like, okay, here's nice new fossil. Um, but a lot of times, even working with the fossils that we already have, there's a lot of new discoveries to be made, and a lot more in terms of like understanding a very incomplete fossil record. So to get into that, um, bring up an example here. So the famous French anatomist from the early 19th century, Baron Cuvier, sort of the legend was at least that he said he could reconstruct an entire animal from a single bone. Um, and in some cases, yeah, he got things pretty close. But like so many times in the history of paleontology, it has been shown that there's lots of errors in trying to interpret what is necessarily a very incomplete fossil record. So to take one classic example here, so this is the original material of the first dinosaur sort of to be discovered, Iguanodon, which was found in the early 19th century in England. And so originally on the basis of just teeth and then a few parts of the skeleton, which was used to reconstruct it really as an enormous, like proper rhinoceros iguana, with a horn on the tip of its nose and sort of a long lizard-like tail, such that when early paleo artists, tried to put it together, they made this really monstrous-looking lizard with sort of like smiley, sharp teeth there. And from a modern perspective, of course, we know this is ridiculous. Iguanodon, we now have complete skeletons of, and it is a, perhaps facultatively, so sometimes bipedal animal, so not always on four legs. And that horn on the nose is actually a spike on its thumb. Its tail was very, very rigid and upright, not sort of this long loop-de-loop like the lizard. And rather than having those sharp teeth, it had sort of grinding teeth for eating plants because it was a big herbivore. Um, so a lot has changed in Iguanodon over the years. But even more recently, so I mean, a lot of the Iguanodon skeletons were found in Belgium already at the end of the 19th century. But looking at a more recent discovery, and this is one that has happened even sort of within the span where we've been doing old news, there's the famous Mongolian dinosaur Dinochirus, which for decades was only known from this one pair of gigantic clawed arms. And early on, some people thought, oh, maybe it was like this real super predator, just like, this 20-foot tall kind of, here it's almost depicted as kind of a humpbacked monster, which is kind of like dangling claws for grabbing up whatever unfortunate little dinosaur happens to walk by. And of course, now we know that this is equally false as that sort of rhinoceros iguanodon, thanks to nearly complete skeletons of Deinocheirus that have been found in Mongolia in recent years. We know it's actually more bizarre than anyone ever imagined. It did turn out to be humpbacked, oddly enough, but it's an ostrich mimic dinosaur, an ornithomimosaur, with this long duck-billed skull, almost more like a hadrosaur than a theropod. So this very specialized kind of giant herbivorous ostrich mimic. So really, had no idea about what Deinocheirus was really like until we found more of the skeleton. Um, so there's this gap in just being able to reconstruct the complete anatomy based on the incompleteness of the fossil record. But also when we're thinking about paleobiology, which is how these animals lived, there's also the question of trying to reconstruct fossil behavior. So uh, and often, like, the attempts at this are made based on ideally complete skeletons where we can use our basic knowledge of anatomy to try to look at muscle scars and see sort of what things would attach to what, and what bones are capable of rotating in their sockets to a certain degree. And we can make some fairly good educated guesses about that. But even, working from museum mounts can be somewhat difficult. So, I mean, here, this looks like a complete skeleton of this juvenile horned dinosaur, Brachioceratops. And it looks like all the bones are there. But when you look at the historic photos of it actually being constructed, you can see that actually the majority of the bones, the ones in white, are plaster reconstructions that were modeled to put the skeleton together. And so there's only little fragments there. So that's one sort of issue we have to deal with. But even when we do have a complete skeleton, so for example, let's talk about like long neck dinosaurs, the sauropods. Um, we've more or less known what the whole skeleton looked like since the 1800s, give or take the occasional uh, mismatched skull that you may be familiar with from sort of the whole Brontosaurus debate. Um, but in trying to interpret the behavior of those animals based on the same set of fossils, over the past 100 years, we've gone from these kind of lumbering swamp dwellers to obligatory aquatic animals that would have been in the water all the time to being up on land, but dragging their tails on the ground and having their heads sort of sunk down low to the ground, to potentially even rearing up on their hind legs. And so some of these earlier ones have now been, on the basis of like basic physics, have been shown to be inaccurate. But there's still a lot of debate over these other more recent poses. Like, could Barosaurus, the animal depicted in the bottom left there, really take a tripod stance? Like, is that physically possible? Is it biologically likely? Even if it could do that, would it have done that with any regularity? These are things that have been hotly debated by paleontologists. And in order to try to, get at answers here, we need to look beyond kind of the skeletons. Of course, some of these things like truly are unknowable. We won't, short of a time machine, we won't be able to see how these animals really lived. But there's a lot that we can do as scientists to sort of improve the educated guesses we make about dinosaurian in this case, but also this applies to all prehistoric organisms, their paleobiology. So let's take a case where we actually do have total knowledge of a part of the skeleton, which is the head and neck of Tyrannosaurus. So between the dozens of known specimens of Tyrannosaurus, we really do have each of these bones represented. So we're very confident about sort of what this is. Sorts of things you can do, like in terms of orienting the vertebrae and seeing how the lower jaw articulates with the skull, and trying to figure out potential ranges of motion and figure out sort of how this animal would have moved around and fed. Um, but even knowing every one of the bones, there's obviously like a lot missing here that would be present in the real animal, right? Or in the living animal, I should say. Because if you compare to a recently living animal, so this is a cross section through the head and neck of a horse, there's of course there's all the meat, right? So muscle tissue, tendons, ligaments, nerves, sinuses, all of these things. Um, and so even just thinking about how the bones move to relative to one another, which is sort of one of the most basic things we can do in terms of the functional anatomy of a dinosaurian skeleton. We don't just have to consider the bones. So here in this cross section of the horse, you can see here's one of the neck vertebrae there, sort of those tannish structures. But if you look at the white stuff in between them, so that's the cartilage, which actually sort of protects that articulatory surface as that where the bones are moving and bumping up against one another and facilitates their motion. So there's not bone on bone for the most part in living animals. I mean, you hope not. I mean, it's usually bad news for you when there is a lack of cartilage at a joint. And without being able to understand how these soft tissue structures, be it both sort of cartilage and other connective tissues, as well as the muscles, influence the range of motions of bone, we can't really say how something like an extinct dinosaur would have moved around. Um, so there are some ways to get around this big problem that we have about lack of data. And so an important one is the phylogenetic bracket. And really all this means is that you look at the family tree of a group of organisms and you see sort of what is related to what, and then you use that to infer things that you can't see in the actual fossils. So here's just one example. So this is three birds. So you have on the left the first bird, Archaeopteryx, on the right, living birds represented by a pigeon. And so then in the middle, you have this animal Hesperornis, which is a Cretaceous marine bird. And all we have of Hesperornis is the skeleton. We don't have any soft tissue. We don't have any integumentary impressions. So did Hesperornis have feathers? Well, we know Archaeopteryx has feathers because of that wonderful fossil from the Zollenhofen Lagerstätte. We know, obviously, modern birds have fossils. So by bracketing Hesperornis between these two parts of the tree, we can fairly confidently say that Hesperornis would have had feathers. So this is just the basics of using relatedness to say what may have been present, even though we can't see it in the fossil. And you can do the same with muscles and nerves. And so a lot of this has been done, especially with birds and alligators, when we're thinking about dinosaurs. And what's the reason for that? Well, birds are living dinosaurs, as we've discussed many times. They're descended from Mesozoic dinosaurs. And crocodilians are the closest relatives sort of outside of that group. So they're the closest archosaurs, these ruling reptiles, to the bird dinosaur group. Things like lizards, snakes, turtles, mammals, amphibians are all more distantly related to them. So if you see, this is just one example, the course of jaw musculature in alligator. If you compare the jaw muscles of an alligator and the jaw muscles of a bird, you can place, what dinosaurs would have been doing somewhere between those. So you can sort of ground truth your hypotheses of what dinosaurian muscles would have been doing based on their closest living relatives. But we can do even better than that. So a lot of this historically was done by dissections of dead specimens. And that's, extremely valuable work. And there's a huge amount of anatomical data that has come out of those sorts of dissections. But, it still gives you sort of a static view of what's happening in an extinct animal, which is already sort of, an extremely static object. It's just fossils. And this is where new technology is really coming to the fore and giving us more insight than really we'd ever imagined into the motion of living animals and then helping us extrapolate that of extinct animals. So one way, which was the subject of this talk at SVP, that has really been adding a lot of new information is what's called XROM, X-ray reconstruction of moving morphology. So X-rays, have been used for a long time in the medical fields, and always are getting more advanced. But I think still, even nowadays, when you think about X-ray, you think of the doctor uh, showing you a still image that shows like black background and then just your rib cage or a broken arm or whatever it is that required having an X-ray. Um, for a little while, it's been possible to X-ray things in motion, so using both X-rays and video cameras. What XROM does is really taking that to the next level of adding in the results of CT data, so computed tomographic imaging of the insides of organisms. So here on this figure, this is just a basic XROM setup where you have two sources of X-rays that are being shown like directed towards this rat, and then a pair of cameras that let you see the bones basically moving around. And you can do even better than that. So this is a very complicated setup, which is the basis for the work we'll be talking about in just a second, where you have this animal moving on the surface with 4 different cameras, including 2 X-rays, one sort of like the live action, and then one at this force plate. So this is where it's stepping down, and you're seeing actually exactly how much force is being exerted by the animal's movements. So just collecting a huge amount of videographic and tomographic data on the movements of this animal. So usually what has to be done for this in order to get them to match up, what you're doing with the CT data is basically kind of like rotoscoping the CT reconstructions, these digital reconstructions of the bones, onto the video of the X-ray. And that's usually done by implanting like little metal beads in the animal as it's moving, so you can match up 1-to-1. So you know that the bead is present at this point in the leg, and then you can see that actually show up on the X-ray. And you just map on that CGI image to the video. As you can see in this, here's just an example of what that looks like by the Brown Lab group here. So this is a guinea fowl. This is a small chicken-like bird, originally from Africa, but now used as a food source, really, in a lot of places around the world. And so this is an animal that is moving slowly and is sort of juking around in its ecosystem. So this is a test to see sort of the limits of its mobility in a complicated landscape. So you can see the black and white in the back there is the actual X-ray, and then they've mapped on kind of in yellowish there the actual CG reconstruction of the bone. So again, you can see here's the like the live image of it. And there's that CGI mapped on as well. So you can do this both in the X-ray footage and the live footage because they've been taken at the exact same time. And you can see they're kind of like shaking latex gloves at this little bird because, again, they don't want it just running straight in one direction. They're trying to see what's happening as it's navigating a complex landscape. And you can just look at the bones themselves in isolation. And this is really sort of what gets at direct comparisons to fossil organisms where we only have the bones. So if we can see how the bones move during typical locomotion in a living dinosaur, a bird, we can start to figure out how that's going in an extinct dinosaur. And so this was the basis for the whole research program. That was the subject of the Romer talk, looking at joint mobility in both birds and crocodilians. So in this case, you can see the guinea fowl in a running posture on the top and the alligator on the bottom, to figure out basically what's possible for dinosaurs, like what makes sense in terms of how a dinosaur can move and what is just like out of the range of possibility for them. So if you just compare, here's the XROM footage of these two, and you can see while it's still the little dark flecks in there, so those are the the implanted little metal bits for these animals. Um, and so there they are walking, and there you can see the CT reconstructions of their bones inside. And so there's that phylogenetic bracketing where if alligator is doing it and the bird is doing it, we can be fairly confident that dinosaurs were also able to do it. Of course, there are tons of caveats to this. Dinosaurs were dealing with force regimes far beyond any living bird or crocodilian, something the size of a brachiosaurus, for instance, things that, are reaching the dozens of tons. Uh, it's not necessarily like possible for a little chickeny thing to be one-to-one, something like that, right? So there's specialized adaptations that they may have had that would have been unique to themselves. But there's a lot that we can take from this. So for example, this is looking at the range of motion of the joints of the bird and the alligator. Um, and then you can map that onto, this is in a more recent paper that came out this year by the same research group. And so you've got, alligator at the base and the guinea fowl kind of at the tip of this tree here. And then you have these three extinct animals in between them, sort of a classic big carnivorous dinosaur, Allosaurus, an extinct giant bird, the recently extinct moa from known from Polynesia, and then this early dinosauromorph Marsuchus, or as it's sometimes called now, Lagosuchus. And so applying the same basically ground truths that were found for both the bird and the alligator to these, and the same sort of muscular reconstructions that we know are present in these living archosaurs, there's actually a lot of things you can learn from these extinct animals. I mean, obviously these are all hypothetical, but sort of within the range of motion that we see in alligators and birds, can infer that maybe, for example, Allosaurus, which is a very big animal, and has very sort of robust and erect limbs, would have had relatively limited mobility around the hips and then a lot more at the knees and the ankles, whereas the very small-bodied and with pretty like lots of cartilage at all of its joints in the Lagosuchus maybe it would have been extremely mobile in all of these joints. It just had a lot less weight that it had to contend with. May have been more agile than sort of this, I wouldn't want to say Allosaurus was lumbering. I mean, it was not like Rite of Spring style, just old like cartoons dragging its tail on the ground sort of thing. It would have been a fairly active animal, but nowhere near the agility that you'd see in like small insect eater like Lagosuchus, or a lot of modern lizards like a collared lizard or these other things that will rise up on their hind legs and just go sort of squirming all over the place. So I think, this is still early days for this approach to paleobiology, but I think it holds immense promise. And clearly sort of the other members of the society thought so as well. We're all like really, really excited by these advances. And really the technology keeps getting better and better. Um, so I think as we are able to, learn more about living animals, we'll also be learning more about sort of the prehistoric world. So I mean, these are not separate. Like paleontology is very much, as I always say, at the interface of geology and biology. Um, and although they're just like rocks now. They were once living things, and we really need to think of them as such. They're not just sort of a set of bones that we put up in a museum to sort of like stand as showpieces, but there's something that we gives us a vision, a window into forgotten worlds, if you will. So anything that helps us improve that understanding, I think, is just great.
Yeah, I completely agree. And in the chat as well, we've got um, just some folk saying that it's incredible. This technology, the live mapping where, it uses X-ray, live footage, and CGI.
Yeah,
It's just
yeah.
incredible. Um, So I've never seen anything like that in action, and it makes me wonder, Christian, I'm assuming since you chose this topic for our episode of Old News, I'm assuming that you have not done research using the XROM technology. Is that correct?
I have not, no.
So if you were gonna be able to use it, what would you do with it? Like, what would you study? Just curious.
Well, I mean, so it's actually of great relevance to my study system because I work, primarily on these synapsids from the Permian period, which really they have no good living analogs, but they are the ancestors of mammals. So we can still, it's going very, very deep. So it's going, 300 million years deep, but we can still use phylogenetic bracketing to help understand some aspects of how they moved. So in this case, what I would probably use would be a representative modern mammal generalized thing, probably like an opossum. Um, and then maybe even something like a salamander, because you have to go so deep, even kind of outside of amniotes. Um, Salamanders are themselves specialized. Like none of these things is just a perfect ancestor, uh, but it's certainly a better example of something outside of uh, amniotes, mammals and reptiles, than like a frog or a Sicilian. The other amphibians are just so hyper specialized in terms of their locomotion that kind of salamander is all we got. And if there are like shared sort of muscular mobility characters between sort of early mammals and salamanders, we can be pretty confident that they were in early synapsids as well. Um, and again, this is just to, like I said, none of this is the be all end all. This is to help inform our hypotheses, help inform our reconstructions of these things. There is also still just like a lot of fundamental like anatomy that needs to be done. So I mean, you can just like I said, you can reconstruct muscles to a degree just by looking at the muscle scars that are on the skeletons. Um, but in terms of like whether these things were able to walk upright, sort of how fast they were able to move, whether they were always sprawling or whether they were like up on their feet. I think these are all topics that, having the XROM data would help us understand what's going on with synapsids. And a lot of it so far has been, focused on dinosaurs and to a lesser extent some fossil mammals. But I think, yeah, it's ripe for pulling even further back into the tree. And there was actually some work from the same research group that recently came out looking at one of my favorite animals, actually, which is a big amphibian from the Permian called Eriops. So already they're starting to look at some of these Permian animals. In that case, they did find that a salamander-like gait would have been possible and maybe even likely for that animal. So yeah, would love to expand that further into sort of the Permian world.
Mhm. Yeah, I bet you could. I mean, we should do that here because, you know, we've got salamanders here at the museum. I don't know if anybody watching has been able to visit, but we're North Carolina. We're the salamander capital of the world.
Yeah,
So, Christian, I will try to help move this along. Christian needs XROM.
yeah, yeah. Just give me a few $1 million to set up this facility here.
It's nothing, right?
Yeah, down in the basement.
Oh, right. So we've got some folks in the chat.
Mhm.
Anne made a great comment that I don't understand. I don't get the reference, but maybe you will. She said that this technology, it's like Arnold Schwarzenegger going through security in the movie Eraser. Um,
Yeah, it's they in that movie they showed the skeleton inside as he's going through.
okay,
Um, yeah, that technology is basically real now.
incredible. Do you know when that movie came out?
Well, it's a while ago now. I think that was in the 90s, right?
It's
Must be
just
like
always interesting to
96,
me
97.
how movies predict, future technology sometimes.
Mm-hmm.
Jack,
Any other questions?
I have a lot of questions, but I do
Okay.
want to also say that Jack added a comment saying that this would be very helpful for designing controls for their puppets. And
Oh,
I'd love to see what that is like. Um,
Yeah. I mean, puppetry as an art, certainly you can go exaggerated for it, but also if you want it very like realistic, yeah, this is a great way to do that.
mhm,
Especially if you're like doing like trying to make dinosaur puppets and really have them feel real and feel like something like that the public think is a living animal.
mhm. Christian, you mentioned earlier speed, like animals' speed, and we
Hmm.
actually had a question from one of our registrants
Okay.
about the velociraptor, their favorite dinosaur. So I know that, this particular research wasn't looking at the top speeds, but I'm really curious, A, if you know the top speed of a velociraptor, and B, how do we even determine stuff like that? Like, what are scientists looking for when they decide on top speed or, you know?
Yeah, so this is something that is what we don't, I'll say upfront, we don't know. Um, and scientists have spent a lot of time debating things like this. So, I mean, you probably know, like in Jurassic Park, like Muldoon says, cheetah speed over open ground. And so, I mean, that would put Velociraptor moving at like 60 miles an hour. That is probably not accurate. That is probably too high. But with theropods, yeah, there have been a bunch of papers written both about, well, Tyrannosaurus for one, and smaller theropods like Velociraptor, that have the results have actually varied wildly, from as much as like moving at 40 miles an hour or really kind of like puttering along barely faster than a human. A lot of it has to do with the muscular reconstruction and also sort of the mass of the animal. So there's a there's an issue between like raw speed and actual acceleration. So like if a Tyrannosaurus Rex, it's so big, it's moving with a stride of like 10 feet at a time. It's still going to be moving relatively quickly compared to us who have shorter legs. Whereas Velociraptor might be moving a lot more footfalls at any given time and have greater acceleration, but still covering less ground. So that's one issue in terms of just like miles per hour. Um, the other thing is that does help inform this though is the really our only direct fossil evidence for behavior in extinct animals, which is the footprint record. So these ichnofossils, or various trace fossils that we have. And so those are a sort of a hard bound for animal speed because we can actually figure out stride length because of that. Um, and also the depth of the footprint is influenced by how much force is occurring as it's basically pounding down. So if you're running, you leave deeper footprints than if you're walking slowly. I mean, if you have ever like run along the beach, you probably notice this. Um, so combining footprint depth and stride length in extinct animals does get us at, one answer of like what it was possible for these things to run at. Um, Now, of course, that's only sort of one behavior during one day in the existence of this group of organisms. So they could very well have moved faster than that, or most of the time, maybe they were moving slower than that. Um, but yeah, so I unfortunately can't tell you exactly like Velociraptor definitely 45 miles an hour all the time. Um, but yeah, I think I mean they both those animals, both T-Rex and Velociraptor, do have relatively long limbs. So I think that would be fairly speedy. Probably comparable to maybe something like a coyote. This is so moving into the realm of speculation here. But I think that that's reasonable.
And Christian, you said a word that I did not recognize earlier. Was it ichnofossils or
Oh,
ichno?
ichnofossils are just the sort of the technical term for trace fossils.
Okay. Yeah. So trace fossils, including like the footprints you were talking about, fossilized dung,
Yep.
uh,
Burrows, bite
burrows. Yeah.
marks, anything like that.
Anything that's
Uh,
not an actual body part that
yeah.
became a fossil. Yeah.
all
Okay.
the all the results of extinct organisms behavior that's reflected in the fossil record.
All right. And our next question from Jeff. Are there specific animals to X-ray that are, or X-ROM, that are a close analog to dinosaurs?
So I think they're doing really the best with what they already have. So, I mean, birds and crocodiles are the way to go. Um, there are also practical concerns. So if you're looking at a big dinosaur, maybe you would prefer to look at a big bird like an ostrich or an emu or something rather than a little guinea fowl. Um, but you have to keep in mind where you're going to get an ostrich, how are you going to get it into, your little treadmill set up in the basement of your lab. Keep it sedated and restrained while you're sort of implanting the marker beads. Fit it ideally alive through the CT scanner. So, I mean, you can use like their medical CT scanners. A lot of people go through. I mean, I've been through a CT scanner myself. So, but I'm not as big as an ostrich. Uh, so there's very limited, like there are veterinary CT scanners too, where they put cattle and things through, but it's those can be hard to get a hold of. So all of like there are real practical concerns to this. And so I think as long as you're within that phylogenetic bracket and the animals are doing sort of what you expect the extinct things to do, like if you had a penguin in there, I think that probably would be a bad analog for these dinosaurs. I mean, penguins are so specialized for deep diving. You can argue even alligators are being semi-aquatic are not great, but all living crocodilians are semi-aquatic, so we're kind of stuck there. Um, Ideally, I mean, you'd also be, the phylogenetic bracket is very important, but you do also want to take uh, evidence from things that are maybe convergent on some of these. So, like if you're looking um, at one of these, bat-winged dinosaurs that we've discussed before, maybe look at some modern gliders as opposed to sort of the powered flight of most birds. So they may have been doing a few things that like their brackets aren't doing, like just like I talked about before with Brachiosaurus and these super giant ones. Um, but really, I think that the research groups that are looking at this, they're making the best initial choices, at least for figuring out basically the ground rules of how these things move, and then can start to look at more specific problems that are more taxon focused.
Mhm. Yeah, so going back to that research, it sounds like they collected a ton of data by the end of it. I mean, if because I didn't realize that the guinea fowl was walking on a force plate as well.
Mhm.
So I'm imagining that this research team has, lots of numbers that they can play with. And when I say play, I mean like analyze. So do you think that like is that the plan? Is that kind of the next step as far as this research goes? Is to like analyze those data, or is it to do this use these techniques and what we learned from doing this and do it again but with different animals? Like what do you think are the next steps?
Oh, I can say it's definitely both. So yeah, that's a huge amount of data. They've collected just terabytes and terabytes of data. All this, it's super high speed video from 6 different cameras, and then also all the high resolution micro CT data that they have. And then on top of that, any um, physiological, when they have, it wasn't shown in this, but sometimes you can hook up the animal so that you're monitoring its oxygen while it's doing all this stuff, um, and force plate, things like that. Um, so yeah, I think it like that data will be used for years and years in different projects because there's so many different questions you can help address with that. And probably like students in that lab will be making use of that data for a long time to come. But yeah, I know they're also sort of expanding their scope to other organisms. Like alligator and guinea fowl have worked well, but you need to make sure that what your study system isn't like just totally weird and atypical for the group in general. I don't think they are. Like I think, like I said before, I think those are good choices. But you want to test, is a duck doing the same thing? Are sparrows doing the same thing? And these are topics that are being very
Mhm.
actively pursued by these research groups.
Very cool. And so it may be, too early for them to have looked really intensely at the data. I'm not really sure, but have they learned anything new about, the dinosaur motion? Have they learned anything new yet? Have they been able to, you know, look at their findings and realize, oh, turns out dinosaurs couldn't do this thing that we thought they could do.
Uh,
Um,
y- I'd say yes. I mean, they absolutely have, the paper that came out this year was very much like trying to use this data to figure out range of mobility in Allosaurus. Um, I wouldn't say that they've found any like they haven't overturned any like existing hypotheses to a great degree. Like there's no uh they didn't figure out that like Tyrannosaurus was actually quadrupedal or anything. Um,
that'd be
there's
wild.
for, but keep in mind that like theropod dinosaurs are some of the most studied, some would say overstudied groups of fossil animals there are. So there has been, from the functional anatomical standpoint, they have been under intense scrutiny for decades now. So if there's any group where we would expect that they have probably gotten things mostly right already, it would be that. So the new data is, some of the best evidence yet that, yeah, how we are envisioning these things moving is probably pretty okay. I think what's going to get more interesting is when it starts being applied to groups that have not been under the microscope as much. There was also some very cool work presented at SVP about some of the herbivorous groups of dinosaurs, both horned dinosaurs and the dome-headed dinosaurs, pachycephalosaurs, that would have some major implications for kind of shaking up how we think they move. So can't talk about that research yet because it's still in the pipeline. But yeah, and those are things that also, will have to be tested against sort of the actual musculature and motion of living things. And in those cases, I think there will be some pretty big shakeups in our views of these animals.
Mhm. Um, so I'm seeing a question from Jack saying, could it still walk like a bird? Um, Jack, are you referring to like a T-Rex or, the typical dinosaur that we think of when you say it? Um, and while you're answering my question, Christian, I'll give you another question from the chat from
Mhm.
Anne. Is this technology being used in medicine right now that you know of?
Yes. Well, so the X-ROM stuff I actually am not sure, but the uh, the X-ray techniques were initially designed for human medicine. So like so much of our imaging technology is based on the medical world because one, I mean, we need like us continuing to stay alive uh, 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 is more important than figuring out how dinosaurs moved. And also, there's much more money in it than figuring out how dinosaurs moved. Uh, Having something that you can sell to hospitals and all that. So yeah, all of the like motion-based X-ray technology is originally looking at humans. The X-ROM stuff is so there's what's called like rotoscoped X-rays, which had been done with humans earlier, but the like proper, doing full CT reconstruction of the skeleton and then mapping it onto the X-rays is really kind of novel to looking at these non-human organisms. Because we basically have a pretty good idea how humans move already. Like we don't really need that basic information. Like we know, like I said, that theropods are intensely studied. Like no single species is more intensely studied than ourselves. Um, so, I mean, you don't necessarily need to do XROM to know how humans move. But there's so much basic behavioral and anatomical information on basically all of the rest of life uh, that we're getting now through techniques like this.
Yeah. There and in the chat, our participants are throwing in even more suggestions for how to use this. So yeah,
Mhm.
maybe one day this will be, in households the way that 3D printing is becoming a household technology.
Yeah, maybe it'll be in Schwarzenegger's house, so we can make sure he doesn't have any. Any
I'm sure he
dangerous
already
pets?
has something
Yeah.
something weird like that. Um, all right. So I think we have time for just a couple more questions before we say goodbye.
Okay.
Going back to Jack's question earlier, could it still walk like a bird? That is about a T-Rex. So yeah, do you think did it walk like a bird?
Yes, I think more like a bird than anything else. So
Okay.
like the real answer is it walked like a T-Rex. Like no animal is exactly the same as another animal. But birds by far the closest to how it would have moved. Um, Again, probably just because it had so much more weight, having to deal with maybe a slower pace than, say, an ostrich. But also keep in mind, like T-Rex, its proportions changed a lot during growth. So, like younger T-Rexes had longer, thinner legs, and probably would have been running a lot like big ground birds nowadays. So, emus, ostriches, rheas, all those. Um, so a few differences in terms of like because T-Rex still had the three toes on the ground, and so modern birds, some of them have very asymmetrical feet. Like the ostrich only has two toes to aid in running. But again, broad strokes, I think it's a good point of comparison.
Yeah. And often when I see people like my coworkers doing dinosaur impressions, we end up doing like a neck
Uh-huh.
bob thing, like a chicken.
Yeah, yeah.
Do we think that dinosaurs actually did that?
Well, I mean, why
Okay,
not?
when I say dinosaurs, let me say T-Rex. Do we think T-Rex might have done something like that?
Oh, why wouldn't it? So many birds
It's
do that.
it's got a thick neck and the shorter neck. I don't know. Feels
Yeah,
like
but I mean, when you look at a penguin, the neck is even I mean,
hmm,
looks
that's true.
thicker. There's a whole, like if you look at a penguin skeleton, there's a whole elongate, very narrow set of vertebrae buried under all the fluff and blubber of that. Um, but they're bopping their heads around when they've got the
Yeah.
happy feet. So
Uh,
yeah, I think head bobbing T-Rex, sure.
uh, I think after this, I'm gonna have to watch some videos of like cute penguins.
Yeah.
It's given me a craving to, see some cute birds. I'm gonna end it with one last question. This is from Tam, and it's about the footprint fossils or
Mhm.
just footprints in general. So, are footprints mostly in soft substrates, and would they be quicker on harder ground? I guess this is kind
Yeah,
of, yeah, go ahead.
yeah, that's a good question. So the footprint fossils that we have, yes, are mostly from soft substrates because those are just where they're most easily preserved and most easily found. So the basically the more discrete, the more sort of the sharper the outline and the deeper the footprint, the more chance it has to survive basically to the next day. So not get blown away by sand or trod over by other animals. And the more obvious it will be to paleontologists, because again, to find the footprints, we just have to see them. We have no like way to find them with technology or anything. We just need to be able to make out the outline as a fossil. Um, and so if they're walking over like rocks, if they're walking over really like compacted dirt or grassland, they're just not going to leave footprints, so they'll never be fossilized. Um, and in terms of what was the second part of the question? Sorry.
Sorry, I muted myself. Would they be quicker on harder ground? So like
Oh yeah, yeah.
compacted.
Yeah, yeah. Yes, probably. So, I mean, think about, if you're running through sand versus running on blacktop, you're going to move faster on one than the other. You're not getting mired down in sinking into that substrate, be it thick sand or mud or whatever it is. So yeah, definitely faster in general on hard surfaces.
Mhm. All right, everybody. Well, that's the end of old news for today, but we'll be back next month. Mark your calendars for December 13th at 1 p.m. We don't know the topic yet.
Yep.
So if you would like to know the topic, before the day of the program, you can register to receive a reminder email and we include the topic in there. Or you can just join for whatever fun topic we have, because it's always fun, I think.
Hmm.
Christian, thank you as usual for sharing your expertise with us, and thank you to our participants for asking such great questions.
Yeah.
Um, yeah, we have fun, and I did not get bingo. I hope someone played bingo and had better luck than I did. um, all right, everyone, have a great day. We will see you next month. Bye.
See you then. Stay safe out there, everybody.